I'm Anil Kumar. Welcome to this video on Fibonacci sequence. We'll cover many topics within this in details. As you know, Fibonacci sequence is given by the terms 1, 1, 2, 3, 5, 8, and so on, where adding previous two provides you the next term, right? So add previous two and you get the next term. And that is how we get different terms in this particular sequence. Now, it is to be noted that in new books, we have started using Fibonacci sequence with F0, where F0 is 0, right? So even then, when you add the first two terms, you do get the next term, right? And it doesn't really change much. However, remember that F0 could also be there in your book and in the examination. Okay, now we are going to explore iterative rule for Fibonacci sequence, and then we'll see how is it related with Pascal's triangle. We'll do some examples with algebraic operations on Fibonacci numbers. We'll actually derive some formulae. Now these formulae will help you find quick solutions to many of the examination questions, and that's probably key to quick solutions, right? We'll also see the golden ratio. We'll derive an expression, and rather we'll do two ways of finding the golden number itself. Even Fibonacci numbers. Now that is another very interesting aspect which we are going to look into, and throughout this session I'll take examples from previous test papers. So that should really help you a lot. So let's begin by understanding the Fibonacci sequence itself. A Fibonacci sequence is derived by the recursive formula where we are taking the first term f1 as 1 and the second term also as 1. Now the sequence is derived by adding the previous two terms, you get the next term, right? So that is how it is derived. So basically we add previous two terms to get next term, right? So that is how it is created. Here is example 1 for you. In example 1, you need to write the first 12 terms of this sequence, and then there is a question which says, show that the sum of Fibonacci numbers is 1 less than a Fibonacci number itself, right? That is the question for you. So first part is straightforward. We begin with the two numbers 1 and 1, and when we add them, what do you get? 1 plus 1 is 2. And then you add 1 and 2 to get 3. 2 plus 3 is 5. 5 plus 3 is 8. And then continue this operation, getting all the numbers up to 12. Well, here I like you to remember a few terms specially. CF12 is 144 and F5 is 5, right? First few terms are easy to remember, but knowing those values help us in solving many questions, right? So that's the whole idea. Now, let's look into the second part of this particular question, which is show that the number of Fibonacci, so that the sum of Fibonacci numbers, we are looking into sum now, is 1 less than the Fibonacci number itself. So let's find the sum of Fibonacci numbers now. Okay, so sum of 1, this is the first term, we get just 1. If I add 1 to 1, I get 2. And what is 2 plus 2? 2 plus 2 is 4. 4 plus 3 is 7. 7 plus 5 is 12. 12 plus 8 is 20. 20 plus 13 is 33. And when you add 21, you get 54. When you add 34, you get 88, and so on, right? So you can create a table like this, as we are seeing. Now, we have to look into this part that each number in the sum, which is in this particular row, how is it related with the numbers in the Fibonacci sequence itself? Well, as you can see in this particular case, that we have a number, for example, 7. Now, this number 7 is related with another number, 8. It is just one less. Do you see that? All these terms are one less, right? So similarly, we see 33, and 33 is one less than 34, and I'm pointing out at 144 and 143. 143 is one less than 144. You get an idea. So what do you observe here? Well, basically, the terms and the sum is related. And how is it related? Two numbers and getting back to it, right? So from here itself, we can derive a very important formula to begin with, and that is to say that the sum in Fibonacci sequence can be written as f of n plus 2 minus 1, right? One less than this two terms ahead. Do you understand? So, for example, in this particular case, what we observe is that if I want to find the sum for the first 10 terms, in that case, that should be equal to f of 12 minus 1, correct? That is what it is. F of 12, as I was saying, is 144 minus 1 is 143, and that is what is f of 10. Do you get an idea, right? So that is what the f of 10 is. The sum 143, right? So the formula really helps to get the sum of Fibonacci sequence, right? So we created a series here, right? So this is our Fibonacci series. And the series is very much connected with each term. It is one less than 2 ahead of them, right? That is how you could remember it. Now let's move on and look into the second very important concept. Well, let's have an example based on what we have learned, and then we'll move further. So the example for you here is evaluate F11 plus F12 plus F13 so on till F200, right? We can use the formula just derived, which is the sum of these Fibonacci numbers is basically related with the Fibonacci number itself, right? 2 ahead of it, right? But remember, that sequence starts with 1. Here, we are starting with 11. So in this particular case, to solve, what should I do? Well, I'll split the series in two series. One starting with 1 up to 10, and then 1 to 200. And the difference will give me the answer, correct? So I can now write down this particular series F11, F12, F13 to F200 as combination of F1 to 200 take away F1 to 10. And so what we get is this particular required series F11 to 200. Now, coming back to the formula itself, what is the sum of 1 to 200? Well, the sum of 1 to 200 is 202 minus 1, right? The term number 202 minus 1. Similarly, what is the sum of F1 to F10? It is F12 minus 1, and minus 1, as you can see, cancel away. And so what we get here is F202 minus F12, correct? So we get our answer, which is F202 minus F12. And that is how we can actually solve such questions. So I hope you understand how we can immediately apply the formula learned to solve some examination style questions, right? Now let's look into a very common question, which is what is the relation between the Fibonacci sequence and the Pascal's triangle, right? There could be many different ways of interpreting it. However, the very common one is draw diagonals as shown here, right? So So when you draw diagonals, what do you observe? As shown here, we have given you a Pascal's triangle right there, right? So this is the Pascal's triangle given to you with ones on the border, and the numbers in between are obtained by adding the previous two closest, right? Now, if we draw the diagonals as shown here, as you can clearly see, the very first diagonal goes through only one, and the second one also goes through one, so we get the number 1 and 1, right? Next diagonal, which is going like this, through 2, and we get 2. And then we have 1 plus 2 plus, which is 3, right? So likewise, if you draw these diagonals, in that case, what we get is Fibonacci sequence. You get the idea, right? So the diagonal sum of the numbers in the Pascal's triangle produce Fibonacci sequence. That is the relation between the two. Correct? Now, let's get back to some of the formulas which we have learned. The important relations which we have learned are as follows. And then based on these relations, we are going to solve some questions soon. F of n is fn minus 1 plus fn minus 2, right? So that is sum of previous two, right? We could rearrange this. So what you could do is you can isolate fn minus 1. That will be the difference between the next number and the previous number. So many times you may like to rearrange the terms so that some may cancel out and you may get a simplified expression. Okay. So based on this, we have two examples. If I have to write what is f of 242, well, it is sum of 241 and 240, the previous two terms. However, if I rearrange it and write it f of 342 in terms of f of 343, then I have to take away 341, right? So that is how we could do it. Now for your record, in example 3, what we are doing is sharing with you a formula. It is the explicit formula for Fibonacci sequence. You can use this formula to produce the series. Here is the formula for you. Using this formula, you can actually produce the Fibonacci sequence, right? So try out these values. Try to get the first 5 terms. Well, the answer is given to you. These are your first 5 terms. When you place the value of n right there, you're going to get all these answers, right? So I hope that is going to help you to produce the sequence. Now let's take the next example, which is we are now looking at this particular Pascal's triangle when it is placed in a different format. So we are putting it like rows and columns, so that it becomes slightly easier to interpret the results. So what I've done here is again related the Pascal's triangle with Fibonacci sequence. So as I was saying, if you look into the diagonals, then the sum of numbers the diagonal goes through is actually producing the Fibonacci sequence. Correct? That's the whole idea, right? So that is how you could produce, write down your numbers, and what you get is a Fibonacci sequence. Now, let's have some questions based on what we have learned so far. Example 4 is we will see how to combine the terms and work with it. Find n if f of n is equals to f16 plus 2 times f17 plus f18 plus f19. So we have to find what is this sum equal to in terms of Fibonacci number. So the solution is right here before you. We are going to utilize the formula, which is f of n, the term, is equal to sum of previous two terms, right? So that's the formula which we are going to use. Now the strategy here is this 2 f17 can be broken down and written as f17 and f17, right? And now we can combine the terms and then simplify. So I made this table for you to understand how this combination is taking place. So these two numbers right there, f16 and 17, are combined, and then we are also combining f17 and f18, right? So when you combine 16 and 17, you get 18. And when you combine 17 and 18, you get f of 19. So once you get that, then you can do another level of combination, and that is adding f of 18 and f of 19 should result in f of 20, and then f of 20 with f of 19, we get f of 21. And therefore, the answer for this will be f21. So many algebraic operations in this fashion can be done to solve examination style questions. Now, another very important aspect of Fibonacci sequence is the aesthetic sense. Now, these numbers actually relate to uh, golden rule and golden ratio. Let us see how. So here is a question which will make you go through that. So it is the Fibonacci sequence is defined by the recursive formula as we have seen earlier, starting with 1 and 1, add previous two terms to get the next term. Again, we'll write the first 8 terms, but this time calculate the ratio of the consecutive terms. So what we are trying to do here is we're trying to find ratio of consecutive terms. Okay, so consecutive terms means what comes next over what is there, right? So that is what it is. In short, it can be written as Tn over Tn minus 1, the previous term, right? So that is what we are going to do. Now here is the sequence for you. 1 to 12, that means from 1 to 144. And then what we are trying to do here is just finding this particular ratio, Tn over Tn minus 1, right? So in the first case, what we did was we did 1 over 1 and we got 1, then we get 2 over 1, we got 2, and then we did 3 over 2 and we got 1.5, and then we did 5 over 3, 8 over 5, 13 over 8, correct? Likewise, we continue. And the end, what we did was 144 over 89. Use calculator, round your answer to 3 decimal places. So when you do that, you will observe that the value is approaching to 1.618, right? So the value which we approach to is 1.618 as shown here, right? So that's the value which we approach to. So that value is of great significance. It is called the golden ratio. So the Fibonacci sequence actually leads to golden ratio. So many times when we use dimensions of things, buildings for example, they are in this particular ratio, which is given by the numbers, consecutive numbers within the sequence, correct? That's the whole idea. Now, how do we get it? Here is a proof for the same. So to get to the golden ratio, what we will do here is go with the basic definition of golden ratio. Golden ratio is defined by a point on the line segment AB. So I have a line segment AB and we have a point C on this. So golden ratio is defined by a point on the line segment AB so that phi, now phi is always used as a number for, as a symbol for golden ratio, okay? So we use capital and the lowercase also. So the lowercase is used for the golden ratio directly, and the capital one is 1 over phi, right? So we have two phi's which we normally use. So that is the capital phi, right? Which is normally equals to 1 over phi, right? So that is the, and the golden ratio when we talk about is phi, which is 1.618 approximately, correct? So that is the ratio which we are looking into. So let us see the derivation of this. You say this word as phi, P-H-I, correct? It's a Greek symbol and it is standard symbol for golden ratio. Now how do you find golden ratio? You take a line segment AB, a point on line segment AB, which we have taken as C. Now golden ratio is defined as phi equals to AC over CB. So this length AC over the smaller length CB. So that is the golden ratio, right? So we have written here phi is AC over CB, which is x over 1 minus x. This is one way of saying it. The other way also is is that this ratio is also equals to AB over AC. So AB is the whole length, which is 1. We have taken 1 in this particular case, over A to C, which is the larger length, right? So AB over AC, 1 over X. You get the idea, right? So that is how it has been defined. So the question is, compare it with the ratio of consecutive terms which Fibonacci sequence approaches. And we know it approaches what value? We already found it approaches 1.618, right? So that is what it approaches. So we'll compare it with the same value. So now to prove it, let us consider a line segment AB of unit length. So A to B is 1 unit long with a point C. If AC is X, then CB will be 1 minus X, correct? So CB will be 1 minus X. Okay, so as defined, the ratio, we have phi is equal to X over 1 minus X equals to 1 over X, correct? So as you can see, phi is equals to 1 over X, right? Now, to solve for phi, we can actually solve for X. So what we will do here is we'll solve this particular equation, which is X over 1 minus X equals to 1 over X. When you cross multiply, you get a quadratic equation X squared equals to 1 minus X. Bring the terms together, X squared plus X minus 1 equals to 0. You get a quadratic equation, very simple form. Solve using the quadratic formula, right? So I hope you remember the formula, which is minus b plus minus square root of b squared minus 4ac over 2a, right? So that is the formula when you use with the quadratic equation ax squared plus bx plus c, right? So in that case, this formula is to be used. And we're using the same formula here where we know a is 1, b is 1, and c is minus 1. Substituting these values, minus of b plus minus b squared minus 4ac. That minus 1 makes it positive, and so we get within the square root 1 plus 4. And so we get minus 1 plus minus 5 over 2 square root. Remember, we are comparing lengths. Since we are comparing lengths, we know x has to be positive value. So when you use the calculator, you get a value which is 0.6180 something. When you divide 1 by this value of x, you get the golden ratio phi. Is that clear to you? Now this ratio is almost same, exactly same for 3 decimal places as our Fibonacci sequence, correct? So that is how we actually prove it. So this is one part of the proof where I took AB as one unit. It makes things simpler to do. Now here is another part of the same proof. So we'll go through the second proof, right? So many times that is preferred to second proof. So in this case, what we have done is we have taken a line segment AB with a point C, of course, where the distance is A and B, a general case. So we have taken a very general case. Okay, so again, the ratio AC over CB, which is this, right? So you could also remember this as large over small, right? Large over small. So larger length is AC over the smaller length, which is CB, is equal to AB over AC. AB is the whole, right? So whole over large. So that gives you the equation to solve, right? Then you solve the equation. Is that clear to you? So that is what we have. So what we have is we have A over B equals to A plus B over A. So you can simplify this. A divided by A is 1. So you get B over A. Now since phi is equals to A over B, B over A can be written as 1 over phi, correct? And therefore we get our equation phi equals to 1 plus 1 over phi. Is that clear to you? So that is how we get our equation directly in terms of the golden ratio symbol phi. Now cross multiply, and there you get a very good polynomial equation. This equation is the simplest or the minimal. We can write minimal polynomial, right? So it is also known as, it's already mentioned here in my slides. So let me just highlight that. Okay, so this particular equation is the minimal polynomial. Here, phi is the golden ratio. So again, use the quadratic formula, and when you get 1 plus square root of 5 over 2, taking positive value, we directly get our answer 1.618, right? So that is the golden ratio, which is exactly the same as the number approached by the Fibonacci sequence, correct? Now, let's take some more very interesting questions, algebraic methods to work with Fibonacci sequence. Example 7. Sum of odd or even terms in Fibonacci sequence. So many times in examination, you will have questions based on this particular concept. So prove the following: f1 plus f3 plus f5 plus f7 plus f9 is what? That will be the question most of the time, while it is the even number f10. Okay, that is first part. Second is f0 plus f2, f4, f6, f8 is what? So basically, we have two examples for you. In the first one, we're talking about sum of odd, right? Sum of odd terms. And then the second one, we're talking about sum of even terms. Is that clear to you, right? And let us try to understand the strategy to solve such questions, right? So let's look into the sum of odd terms first. Okay, so what have we done here? f1 plus f3 plus f5 plus f7 plus f9 equals to f10. Since we want to get that f10, it's a good idea to rewrite each term as f9 is 10 minus 8. Do you see that? So basically what we did was, you know this particular formula, fn is fn minus 1 plus fn minus 2. Rearrange it, right? So when you rearrange it, bringing fn minus 1 to the left side, we can get f minus n minus 2 to the left side. We get fn minus 1. So you can write fn minus 1 as the difference of fn and fn minus 2. That should help you, right? So what we are trying to say here is f9 could be written as f10 minus f8. So that's what I did. f9 is written as f10 minus f8, and then we took up f7. f7 will be written as f8 minus f6, and then we took f5. f5 will be 6 minus 4, and likewise you can continue with all the terms, right? So in this particular case, these are the terms and they are written with difference of Fibonacci sequence numbers. So as soon as you write that, you can notice that many of the terms cancel away. For example, f of 8 cancels with minus f of 8, right? So that cancels. Similarly, f6, which is with minus sign, cancels with the positive sign, and f4 cancels, f2 also cancels, right? So likewise, you cancel these terms, and what you're left with is f10 and f0. f0 is 0, right? And therefore, the answer is f10, and that is how you can show this. Perfect. So when you are adding these odd terms, that could be the strategy. Now let's look into the second strategy for the second case, in which case we are adding the even terms. So in that case, what did I do? Well, it is quite similar. So we split the numbers once again. So in this case, f of 8. f of 8 is written as, so we left f of 8 as such, right? So what we did was, f of 6 was written as a combination, right? So f of 6 is written as, let's go to this place, f of 6 is written as f7 minus f5, the difference of the two, but we left f8 as such, right? So let me say f8, because f9 is our result. So if I get f7 and f8 combination, I'll get f9 as my result, right? That's the whole idea. Okay, so f4 is written as difference of 5 and 3, and then again we took f2 as difference of 3 and 1, and f0 is 0, so just leave it as such. So when you do this, you see many terms get cancelled once again. f0 is 0, right? And the other terms cancel, so you're left with f7 and f8. When you add f7 and f8, you get f9, which is the required answer. So you see there are two different strategies with which we work, and so you can get any question related to this topic very easily. Now let's look into more of such algebraic simplifications. Now here we have a question which says, again, a strategy for working with Fibonacci numbers. The question here is, fill in the blanks. F of 10 is equal to something times f7 plus something times f6. And what is that number which will come there? And similar, we have three examples here. Let's see how to work with the strategy. Now, f10 should be written in terms of f7 and 6. We can go back and back, right, twice or thrice to get into this. So first we'll begin with writing f of 10 as f of 9 plus 8. Now, you can write f of 9 as combination of 8 and 7, right? So 9 is written as 8 and 7, and 8 has been left as such. The idea is to combine the 8s, right? So when you do that, you get 2f of 8 and f7, right? And then again, we're going to now expand these numbers. F of 8 can be written as combination of 7 and 6, and those will be 2 times, right? 2 times 7, 2 times 6. Now again, what you notice is that this 7 and this 7 combined. So you get 3 times f7 plus 2f6. Do you get it? So we get 3 times f7 plus 2f6. So that is first answer here. We get the answer which is 3 times f7 and 2 times f6. So you can continue this operation from here onwards and get further, right? Simplifications. So you are in a position to write f10 in many different ways. So when you continue, you come to the result that f10 could be 5 times f6 plus f3, 8 times f5, 5 times f4, or 13 times f4 plus 8 f3. Now here is a very interesting result. You can compare these numbers and see how you can make a general formula. Now here is the general formula for you, right? You can see how it works. So if I take the combination, what is this f3, f5? Well, these numbers are related with the numbers in the Fibonacci sequence, correct? So let's take any one of these examples. Let's go with this. 8 f5 and 5 f4. So 8 is the term which is basically f6, right? So we get f6 f5 plus 5 is the term which is f5. We get f5 f4. Okay, so that is what we get. And what are we getting out of it is f of 10. So this is equal to f of 10, correct? So you can see how f of 10 is related with these products. So 5 plus 4 is 9, and 6 plus 5 is 11, and 10 is in between. Do you see that? Right? So similar is the case with the next one also. So we're talking about now difference between 10 and 3. So another way of interpreting the same thing is, what is 10 minus 3 equals to? 10 minus 3 is 7. And what is 10 minus 4 equals to? 10 minus 4 is 6. So if you look at these terms, do you see 8 and 13 there? That is how you get the coefficients. And so we get our general formula, which is mentioned right there. Very, very important formula. So I'd like you to pause the video at this stage. Copy this formula, right? Fa plus n plus 1 is equals to Fa plus 1 times Fn plus 1 plus Fa Fn, right? So you can take the last term as Fa and Fn, and then the previous to that add 1 and 1 to both of them, and then to previous to that, fa plus n plus 1, right? So that is how you get your formula. You can actually figure out how far you are from the number. That gives you an idea. So this particular method of figuring out is a very interesting way of doing it. Okay, so let's move on and take some more examples based on our learnings and the formula derived. Here is another question for you. I'd like you to pause the video, answer this question yourself, and then go for the solution, okay? Now the question here is, f of 400 is equals to a times f of 390 plus b times 391. Find a and b. How will you do it, right? So you can pause the video, answer this particular question, and then look into my suggestions. The formula is also given to you for reference. So the strategy here is what we could do: 400 take away 390, and that gives you 10. We could also do 400 take away the other term, which is 391, right? 391, and that is 9. So definitely the coefficients are f10 and f9. Do you see that? Those are the coefficients. Bigger number goes with the bigger. So the bigger number is f391. So that goes with the bigger number f391. So this will be f391 plus that goes with the smaller number f390, right? So in our case, 391 is the coefficient of b, right? So this is b for us and that is a for us. We got our answer. Do you see that? So that is how you can actually get your answer, and the answer is right there for you. So a is f of 10 and b is a is f of 9 and b is f of 10, and those two values are written here for you. Perfect. So you can always go back to your Fibonacci numbers and get the value. Okay. Now here is the next example based on the same concept. The question here is f of n is 5 times f134 plus 3 times f133. Find the value of n. So we're trying to do the reverse operation, right? So this time we'll do the reverse operation. So you can again utilize the same knowledge. You know what is 5, right? So 5 is f of 5, as I think you remember, and 3. 3 is what? 3 is f of 4, correct? So we know that these numbers are 4 and 5, correct? And therefore 133, so we have 133 plus 4, right? So plus 4 plus 5 will give us the answer, correct? So 133 plus 4 you could do, right? In that case, what we get here is 137, and to that we have to add the number to get 1, right? So we get 137 plus 1, add 1 to it to get 138 as our answer, right? So 138. So we know n is equal to 138, right? So this implies n is 138. So you see how adding these numbers and understanding the formula helps us to immediately provide the solution. Perfect. Now I've added a very important concept here, and that is to look into the even numbers in Fibonacci sequence. There are very few even numbers in the Fibonacci sequence. We'll try to explore these numbers and see what is their position. Okay, so the question here is, which of the following are even numbers in the Fibonacci sequence? We're given F13, F14, F15, F16. I've taken simple numbers to just make you understand the concept and also check your values, right? So we know F12 is 144, right? Which was an even number. Okay. Now, so what I've done here is written the whole sequence up to F12. We've been working for it 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Let us see which one of these are even. Well, 2 is even, 8 is even, 34 is even, and 144 is also even. You will notice, what is 2? Actually, F3 is 2, right? And F6 is 8, F9 is 34, F12 is 144. So the even numbers are F3, F6, F9, and F12. clearly the next should be F15, right? So what we see that the even numbers are multiples of 3, right? F times 3 times R, right? So R could be anything. In this particular case, we get C as the correct option. So knowing this particular rule helps you to understand how to quickly get the solution, right? So option C is the correct option. Now, let's look into this concept in further detail since it's a very, very important concept from examination point of view. So here is another question for you which says derive a formula to replace even numbers in relate even numbers in Fibonacci sequence. So we'll now try to see how these even numbers are related, correct? We already know that we have few even numbers and the even numbers are F3, F6, F9 and F12, correct? And they are multiples of 3. How are they related, right? That is what we're trying to figure out now. So, okay, so let's begin with the rule as such. Our Fibonacci sequence term will be Fn equals to Fn minus 1 plus Fn minus 2. So why not write this in terms of F3 and F6? So we'll actually simplify this from the techniques learned. So we'll split these two, both of them in terms of, you know what we did? We just combined them. Fn minus 1 as Fn minus 2, Fn minus 3, and Fn minus 2 as Fn minus 3, Fn minus 4. Uh, so what we did here, let me use a lighter ink here. Okay, so the first two is with Fn1 and then with Fn minus 2. So we combine these four terms. So Fn minus 3 gets combined and we're writing this as 2 times Fn minus 3. Now move further, expanding because we need Fn minus 3 but we don't need the others. So what we are going to do here is Fn minus 2 is being written as the sum of Fn minus 3, Fn minus 4, right? So we did that and we already have 2 Fn minus 3. Fn minus 4 is also written as the sum of Fn minus 5, Fn minus 6. Now from here, what we can see here is that we can combine the Fn minus 3. We got 3 of them there and these two can be combined to form another F3, right? So these two terms, Fn minus 4 and Fn minus 5 are combined. Fn minus 6 is a required number which is also even for us and therefore what we end up with is 4 times Fn minus 3 plus Fn minus 6 is equal to Fn. So from here we can see that if I know that F12 is even, then I can find the next even number. You get the idea, right? So knowing these, we can find the next even number. Perfect. So that is the whole strategy. So the formula here is that the next even number is 4 times Fn minus 3 plus Fn minus 6. You get the idea, right? So in our sequence, if we make a sequence of only even numbers, right? These are even numbers, right? Let's say even numbers, right? These are even Fibonacci numbers. So from here, F3 and 6 are previous to, right? So therefore, I could now write my formula as such as f of n is 4 times f of n minus 3 plus f of n minus 6. And this formula really works. If I have a series which has only even numbers, the series could be F3 is 2, F6 is 8, F9 is 34, F12 is 144. We can find what F15 is 4 times F12 plus F9, correct? So we can find what F of 15 is. F of 15 will be 4 times F of 12 plus F of 9, correct? So we know what F of 9 is and we know what F of 12 is. Adding them up, multiplying by 4 first, gives us the next even number in the Fibonacci sequence. You can repeat this formula again and again and expand your sequence. So 2584 will be the next, and that is how you could actually get, in this case, we did 6 numbers. So you could go on with this series. You have now a golden rule, which is 4 times Fn minus 3 plus Fn minus 6. So we'll kind of end here. We have learned a lot about Fibonacci sequence. In my playlist, you will find many application questions, especially on like breeding of bees and such examples, which could help us to understand this Fibonacci sequence when applied to real life situations. So I hope it makes sense to you. Feel free to write your comment, share your views, and if you like to subscribe to my videos and learn from me, you can always register and send a request on my email, which is mentioned right there, right? So you can always send an email. You can also register at our website for some free videos and even to learn on one-to-one. That will definitely help. Thanks for your time and all the best.